It's really good to see you all, and I wish it was in person, but it seems not possible. I hope very soon, and I hope you are all healthy and your family, and it has been a tough year. So today I'm going to be talking about, I think I changed a little bit the title, but this is a better title, even though it's essentially saying the same thing. So I'm going to be talking about CUR decomposition, subspace clustering, and motion segmentation. So this is basically three uh, parts, three different topics that are connected. And I will start by talking about the problem of subspace clustering right here, then CUR decomposition, and then finally I will talk about motion segmentation, which connect the two. And before I do that, let me just introduce my collaborators. So Ali Sekman, he is a friend, collaborator, and a former student at Tennessee State. And he actually he had already a PhD from Vanderbilt when we met in electrical engineering, and he decided, well, he likes mathematics, so he did another PhD in mathematics, and then and at the time he was already a professor of computer science, and in fact he became the chair of his department, and when he was working on his PhD in mathematics. And Burak Oku is at Middle East Technical University in Turkey, and he visited Ali, and we got the chance to work together for 2 years, and we're still working together, and it has been great fun. He's a professor of robotics. And Keaton Ham came to Vanderbilt about 5 years ago for postdoc, and we collaborated, and we became good friends, and we have done some of this work that I will be presenting here. So those are my collaborators, and let me say a little bit about. So basically, I'll present pieces of these two papers here. For those of you who are interested to go more, to learn more, you can actually go and check those papers if you're interested. And of course, this was partially supported by the National Science Foundation. So what is a subspace clustering problem? Well, I will explain it. And this has a very long history. And those are some of the people that have contributed, and there are many more. And you can read. So some of the earlier work by Vidal and Ma and Sastry. And you can see there is a lot of people that have contributed in various ways. And there is a tutorial by René Vidal, which is in 2010, and I have a review in 2013 of this and other subjects. But anyway, let me start by telling you what is a subspace clustering problem. It's a very simple problem. You have a nonlinear set, call it U. It's a union of subspaces S sub I, the subspace, say, of Rm, that's the ambient space. And so you have, for example, you have this, say, plane, and you have these two lines. Let's say this is in R3 or R4. But this is an example of this type of space, of set. And what you do is, let's say you suppose you draw randomly some points from this union of subspace. So those black points are drawn from there. And you just, let's say you kind of organize them in this matrix W. So W1 is a vector, maybe this one, and W2 is another vector, maybe this one, etc. And you organize all these vectors that you drew from U in this matrix. And you're going to assume something, although this is not necessary. This is just to simplify things in this particular talk here. So you assume that the spaces are independent. That's one way of saying that the dimension of the sum of the spaces is the sum of that dimension. And the assumption also in here for the subspace clustering, at least for this talk, will be that, and usually what is also done is that all the data that you drew, or the vectors that you drew from this union subspace, are generic. It's kind of, you drew them randomly, although this has a more defined meaning that I don't have to go into that now. It's just like a lot of generic randomly chosen points from this union subspaces. And so what is the subspace clustering problem? The subspace clustering problem is you have these vectors that are drawn from this union of subspace. And the question is, well, you want to know how many of these subspaces do you have? You don't know. How many, what is the dimension? Of course, these are some of these problems are related. What is the dimension of these subspaces? Find a basis for these subspaces. And also take the vectors that you have drawn from here, or somebody have drawn from here, and organize them, group them into those that come from subspace S1, and then those that come from subspace S2. And so basically bundle the vectors, or group the vectors that come from the same subspace together. And that will be the clustering of, that's what we call it, clustering, if you like. It's a labeling problem. So why and how this came about, and where does this have application? It turns out that there are several applications, but two are important ones are the motion tracking in videos, or motion segmentation. And I will talk a little bit more about this at the end, and how the subspace segmentation relate to that. And there is actually a data set that you can find at, which is a benchmark that you call the Hopkins 155 motion data set. And if you find an algorithm to track motions, then you can always try it on this set and compare it to other algorithms. So another application is face recognition. So basically, this is an image that's taken of the same person, but at different illumination, and possibly sometimes different pause. So how can you recognize that this image and this image and this image are actually belong to the same person? This is another problem that that is connected to the subspace clustering problem. I will not talk about this. Maybe I will just allude to that at the end, why this is the case. But those are two problems that are related to the subspace clustering problem. So before I go on, is there any question about the problem of subspace clustering? Okay, so if there are none, I will continue. So the next thing I would like to introduce is
about the subspace problem.
So sorry, I could not hear you.
Can you hear me now? Can you hear me now?
I can hear you. Yes.
Yes, I did have a question.
Yes, go ahead.
Which is, how do you go from a subspace, to the samples or data points? Are you assuming a type of sampling or a probability distribution?
Okay, so in that case, so I'm assuming there is so there is a model, there is some union subspace, and something is either picking up or drawing either randomly by some probability distribution from these subspaces, or just not even randomly. I mean, it kind of doesn't matter. The important thing is, the problem is somebody draws a bunch of vectors from this union subspace, and then they give it to you, and they tell you, okay, can you actually separate these vectors into different groups and each group belongs to a specific subspace. And in fact, could you find these subspaces, etc. So how they come from, they could come from any type of drawing. Does that answer your question? I'm not sure.
Okay, yes, that answers it. And so would you do like a training data set and test data set to look at the generalization?
In this case, I'm not gonna, well, we're going to I'll show you how we can solve this problem. And then there is a test data sets. So this is not a training. It's not like the CNN or NN. It's just there is a problem that we can actually solve, and then we can see if we have solved it well by testing it on, for example, this particular this data set, this Hopkin 155. And you'll see it's really direct solution to this problem. So we can actually solve it, and we'll maybe at the end it'll become clearer. Is that okay?
Okay,
Yeah.
thanks.
And Akram, a quick follow-up question. The role of independence versus dependence, I would think that would kind of naturally split things into two different situations, or is my intuition wrong about that?
So independent and dependent subspaces. So the question is, what does this mean, right? So what is this independent subspaces? So basically, if you want to know what this means, at least it doesn't have to be independent really. It doesn't change too much how you solve this problem. It's a little bit harder when they are dependent, but independent means that I mean that was one way of describing independence. Another way is if you take one vector from each subspace, so one vector from S1, one vector from S2, one vector from S3, and none of them, of course, like one non-zero vector from each, then this set is going to be linearly independent. That's another way of describing that. So and normally, yeah. So that's all. So does it change? It changes a little bit. It's a little bit harder when they're dependent, but yeah, that's all.
All right, thank you.
A problem to solve. Nevertheless, same problem. You don't have to assume that they are independent. So so maybe let me talk a little bit about something we call the similarity matrices in order to solve the subspace clustering problem. So again, you have a bunch of vectors that are drawn from this union subspace. And one way of trying to solve this problem is to construct a matrix that we call a similarity matrix. So suppose you have n vectors, n data points. You want to construct n by n square matrix, let's call it SW for similarity of W, that have the following property. It's called similarity because we want it to be that to be non-zero at entry ij if the vector wi and the vector wj belong to the same subspace, say S sub k. And if wi and wj do not belong to the same subspace, we want to be zero. So if we can construct such a matrix, you can see that that would be a good start to trying to solve this problem. So anytime you have a set of vectors and you can construct a similarity matrix in some way or another, you are basically done, because after that there are a lot of methods, spectral clustering and k-means, etc., that you can use directly to kind of solve this problem out of using this matrix, a similarity matrix. So the whole point is, how do you construct a similarity matrix? And one of the first example of a similarity matrix, or thought to be a similarity matrix, was introduced by Costera and Canade in actually 1998. And they started essentially this business of subspace clustering in some ways. And they were trying to find motion segmentation. So how do you find the motion of objects in video? So one way, of course, is to try to find a similarity matrix like that, and they found something that they call the shape interaction matrix. And what is it? It is they take this matrix W, and they take the singular value decomposition of this matrix W. So this is unitary, and the diagonal matrix sigma. And then they take this this unitary matrix and take VVT, and this is what they call the shape interaction matrix. And the claim was this is a similarity matrix. And in fact, I don't know exactly how they found that, because it's almost true, but it's actually not always true. It is almost true. And in fact, we've shown in one of the papers that except for a set of measure 0, basically, this is a similarity matrix. But we'll talk more about this and why it is not and how you can create similarity matrices. So we were interested in trying to create similarity matrices, and that would be basically what I'll be talking a little bit about. So then, now I want to go to the new subject of the CUR decomposition. So let me tell you, I was at a resident for a special program at the Hausdorff Institute in 2016, I believe. And I went to there was a poster session for some students there, and I went to this poster session. And the student had this poster, and he was talking to me about what he was doing, and say, well, the skeleton decomposition, I can do this, I can do that. I have never heard of this decomposition. I had no idea what it was. And then I asked him to explain it to me. And I found it fascinating. I just thought this is incredible. And I also thought that I was working with Ali and Bura at the time on the similarity matrix. And I sent an, after I understood what it was, I decided it was really related. And we start working on that with Ali and Bura about trying to find how to construct this similarity matrix using that. So I will talk then a little bit about, this is now goes by the name of CUR decomposition. It's also goes by the skeleton decomposition, maybe by other names, I don't know. It seems like it has been introduced early in the 1956 by Penrose, but I have, at least when I was in the Hausdorff Institute, this is the paper, the three people that had worked on this. And let me describe at least what it is. So you have a matrix A, it's an M by N matrix, and you are going to decompose it in certain ways. So the first thing you do, you're going to take a number of columns that you see in red. So you take K columns, and after you do that, you take R rows that you see in blue, and the intersection of the rows and column is some matrix U. So you have K columns, S rows, and so the intersection is a matrix S times K, and there is a theorem, and that tells you that if the rank of A is equal to the rank of U, so the rank of these two matrices are the same, then A can be written as the column times the pseudo inverse of U times R. And this is actually very trivial to prove. It just, I don't know, at least at the time, I have never heard about it. I don't know how many people really know it. I certainly did not know, and it was really, I was very surprised. I'm going to give you a proof. It's so simple that I think it's kind of trivial. So suppose the number of column K and the number of row S are equal to R, are equal, and equal to the rank of A. And so this is a restricted assumption for the moment. And I'm going to assume that therefore U is invertible. This matrix U here, which is the square matrix, in this case where I take K equal to S equal to R. So I'm going to assume, since they have the same rank as A, that this matrix is invertible. And so C is the column of A, and it forms a column, a basis for the column of A, columns of A. So I can write the matrix A as the coefficient written so that the coefficient matrix X, and this is the column of C's case. So this is just writing A in terms of the basis C, right? So the columns of A are the basis in the column of C times the coefficient in that basis. So that's it, that's all. Now you multiply A by, to the left, by a row selection matrix, which means that's a matrix that just selects row of matrices. So there's a matrix that have zeros everywhere on every row, but a one in the correct place. And so you multiply this matrix by A, and you get a row matrix of A. So you have A equal to C times X. You multiply both sides by this selection matrix. PRA is a row matrix. PRC is a selection of rows of the column. That is exactly what U is. So you have R is equal to U times X. X is unknown right now. This is what I want to know what X is. I picked R, I know what A, I picked C, so I know what U is, I need to know X. U is invertible, I know what X is, and therefore I replace X by U minus 1R, I get A is C, U minus 1R. So this is a really trivial proof. The proof when U is not invertible because it's not a square matrix is almost as easy. So this is that. So let me go back to then what is the relation between so before I go on, is there any question about at least what the CUR decomposition is? So any matrix can be decomposed as column times some matrix in the middle times it's some rows. Of course, there have to be a relation between I cannot pick any columns or any rows and any U, but there is a way of picking those. So that's really.
I had a question.
Yes, please go ahead.
Yes, so you mentioned previously about the measure zero part, and is the measure zero the probability density based on the sampling?
Right. So this is more, I would say, a measure zero in the sense of I don't really remember exactly, but basically it's more like measure theory rather than probably, but I guess they are related, right? So the set for which this happened is very, very thin from say some measure. I don't remember exactly what it was. It's not that important, but it's basically never happens, almost never happens. And I'll tell you actually, I'll say more, and you'll see what it really means in just a few examples. If you wait, you'll see that even though it's not quite true, if you raise this matrix to certain power, it's going to be a similarity matrix. So the shape interaction matrix is almost almost all the time, but if it's not, you can raise it to a certain power, it will be a similarity matrix. So this is maybe what I really would like to say. But let me wait a little bit. I don't think I have a really good answer to you about that. So we have, again, what is the relation between the CUR decomposition and the subspace clustering? So again, I have a union subspace. The ambient space is Rm. Those are subspaces in Rm. And I draw a number of vectors from this union subspace. And suppose the largest dimension of Si is Dmax, some number. So just before I claim and I'll show you the relation. So this is just a notation. If I take this, if I take any matrix and I'm going to write these bars to mean a new matrix ij, it's that matrix whose entry are I take the absolute value of the entry. So this is just meaning I take the absolute value of the entries of W. And bin of W ij is just if it's a binary matrix, it's going to be 1 if the entry is non-zero and 0 if the entry is 0. So those are just notation that is going to set up the next result that I am going to talk about. So what is a relation? To do subspace clustering, I need a similarity matrix that will help me do the subspace clustering. How do I construct a similarity matrix? Well, I have a W which is drawn from U. I have this matrix. I can always write this matrix as column time U dagger time R. This is the CUR decomposition. Now, once I write that, I'm going to take the U dagger R, this matrix, U dagger R, and call it Y. And I'm going to construct Y transpose Y. This is the square matrix. It is an n by n square matrix. And this matrix, or I can take the binary of this, of Y transpose Y. In any case, this matrix, if I raise it to the power D max, this is D max, is always a similarity matrix. So that is always a similarity matrix. Now, it could be already a similarity matrix beforehand, but for sure, if I raise it to the power D max, it's going to be a similarity matrix. And once I have a similarity matrix, then it should be relatively easy to cluster, to solve the subspace clustering problem. Although it's not as easy because everything I'm talking here about is when things are not noisy. So, but things can be noisy, and that makes problems difficult. And in fact, I'll talk a little bit about the shape interaction matrix. But so some special cases of this decomposition is, well, you can take your column matrix, for example. It has to have rank the same thing as rank as W, but it can be all of W. So if you decide to take the column to be all of W and the R to be all of W, then you can still compute the CUR decomposition in this case and compute these matrices. And what you get actually is that this matrix Q, which is, if not the similarity matrix, it's almost, let's call it the pre-similarity matrix, is this particular thing. So for this special case, it's just, if you decide to take C to be all of W, this is what you get. If you take the column matrix to be all of W, but Q to be some rows that have rank, such that this row matrix is rank R, then this is the pre-similarity matrix that you get. And in particular, you can actually construct the shape interaction matrix this way, precisely by taking this case. And what you get is that the pre-similarity matrix is exactly that. And therefore, you know that this is a pre-similarity matrix. So it's either a similarity matrix itself, or if you take it to this power, it is going to be a similarity matrix for W. And so really, Kanada and Coursera was basically right. And most of the time it was a similarity matrix. And even if it weren't, it was like a almost. And if you raise it to a certain power, it would be. And that's where you can always use that to after that to cluster things. One of the problems that was known about using this matrix to construct the clustering, that it was, when you had noise, it was a little bit unstable. And that's one of the issues that you always have. So I don't want to go through the proof, it's kind of trivial, but let me talk about, so I said that we have the CUR decomposition allow us to construct similarity matrices for that will help us eventually solve the subspace clustering problem. So how do we do that? Why is that? How do we actually, why it does help us? And why not just use already what is known, the shape interaction matrix? Well, here is why, and here is one way you can use the CUR decomposition to actually solve this the subspace clustering problem in a way that is robust to noise. This is a prototypical algorithm. So let me tell you why. So what you do is you can really construct many similarity matrices. When you have no noise, you just can construct one, and with that one, you're good. You use all kind of techniques to then cluster. Once you have a similarity matrix, there is a lot of ways to cluster the vector together. But if the thing is noisy, there is a little problem. What do you do? Well, one way is to the CUR is you have many possible similarity matrices, and if there is noise, they are going to be a little different. So in some way, by using that, the fact, well, they're different, but because they're different because of the noise. So if you kind of do some sort of averaging or something clever with them, you should be able to have a similarity matrix which is somewhat more robust to noise, and with that, you should be able to do a good clustering. And in a way, this is good because the CUR decomposition is somewhat cheap. So in a sense, you could do other decomposition, which is, for example, you could use something which some decomposition was more robust to noise. In particular, you can do the singular value decomposition and maybe use it in some ways. But this is the cheap way because you can do it very fast. Anyway, so how do you do this? So you have the data, and you pick a number k of similarity matrices that you're going to use. You're going to change your columns. You're going to change your rows, and so you're going to change this decomposition, and every k times, and every time you're going to construct this similarity matrix. And if there are no noise, it's going to be always the same if you choose these correctly. Other than that, they are not going to be the same. And so what you can do is take the median or some sort of average, and you get some similarity matrix that hopefully is more robust to noise. Then you do some thresholding on this matrix, and things should work out. So that is roughly the proto algorithm of how you want to use the CUR to construct a similarity matrix. Finally, I want to show you how we can now segment motion. So let me tell you a little bit about motion segmentation. So this is the plane of a camera, and you have this object is moving around. It's a solid object, and let's take this point P, and it has some projection here on the plane, and this point have an XY coordinate, and after it moves, its projection is here, and it's have its XY coordinate change, etc. And this XY coordinate is changing as this object is moving. And here is something that you can prove. Suppose you take for that point P on that object, you take the coordinate on the first frame of your video, and then the second frame of your video, and you continue, and this is the end frame of your video, same points, but the XY coordinate of the same points. And you make this long vector, let's call it W of P. It turns out that for this, for the object, these vectors that you construct from any points and you put them together on this matrix, they belong to a subspace of dimension 4. So basically, if I take many points of this one single object and I construct these vectors, Then I have a I take these vectors. I'm sorry, this is not a good notation, but let's say this is a set instead of a matrix. This set of vectors is included in some subspace, and this subspace must be of dimension 4. So you can prove that. It's always of dimension less. In fact, it's usually less than or equal to 4, but it cannot be more. So different objects will basically live, the vectors that you draw from different objects lives on subspace of dimension 4 in a very large space of dimension R2n. So this is the connection between basically the subspace clustering problem and motion segmentation, in that if you have several objects moving in a video, and if you could label vectors and track these vectors, then every object would lie, all these trajectory vectors for a single object will lie on subspace of dimension 4, but these subspace of dimension 4 lives are in very high dimension, and you can separate them, and so you can cluster them using the CUR decomposition. And this problem this method that we just showed you, we try to see how it works on this Hopkins 155 motion data set. So this has a lot of different motions, some of them cars, some of them synthetic things, etc. And then you try your algorithm. We tried ours. There is a lot of really different ways, and some of them very, very successful. Some of them, well, not as successful, but let me show you a little bit what that was, what we have done on this. So, so this is, I'm just looking at all, so what do we do? So you have these green points. This is the vectors that we track on this, and the red points are vectors that we track on this, and those purple points are these vectors that are the background. These yellow points are some other. So there are, you can say, 4 objects that can be tracked in this video. What the algorithms are trying to do is trying to say, well, taking these vectors, all these vectors basically are in a big bag, and you want to kind of, they're collected in a big bag. That's one way of thinking about it. And you want to collect the green together and the red together and yellow together. And sometimes you make mistakes. Your algorithm makes mistakes. And so this is one method. And all these methods you have them in the Hopkins 155 there, etc. How well they're doing. So you don't have to repeat that. But so this is the average number of mistakes you do. Of like maybe you say this green really belonged to this, but then you make a mistake. So average mistake is about 10% for this method. This method is for etc. You can see there are all kind of methods here that I don't want to go so much into. This is this one that uses the CUR decomposition, and you can see it's doing really pretty well. Basically, it's doing almost as the best methods here. 1% error, 0.007 median, and you need to also to compare somehow how good it is time-wise. And well, it's, for example, compared to Ransack here, which have a 10% error, this one is fast. We're slower, but we do much better. This is compared to the LSA. It's we do better, but this is and also faster, I think, etc. So no, almost the same speed, etc. So this is just one way of looking at how this method does. and compare it to others. And this is just one of the applications of this the CUR decomposition and this method of constructing similarity matrices using it. So I will summarize basically this talk simply. This is really had been a fun project that I have done and with my collaborator, and it's, yeah, I've learned a lot of interesting subjects looking at this from them and from others. So we so I just introduced, I told you what the subspace clustering problem. This is infinite dimension. There is also an infinite dimensional version of that, and but I didn't talk about. And also how this clustering subspace clustering problem and CUR and the motion segmentation are connected. So essentially, one way of solving the subspace segmentation problem is to find similarity matrices. One way of doing that is using CUR decomposition, and that's it. And I just want to give you a little bit some some references if you're interested to go. So there is a paper by Mahoney and Reynes in PNS that talks about this, that for very large matrices where you have matrices that you cannot really read in memory. And so this is, I think, the point of view there, and how you kind of pick in a probabilistic way, how you pick the rows and columns in such a way that you have a reasonable matrix. René Vidal has a paper and a tutorial that appeared in the IEEE in 2010. There is an interesting way of solving this problem with low rank representation and essentially successful one. And it turns out interesting, although I didn't talk about it, this is actually some of these low rank representation that use minimization techniques. So CUR can give you the solution relatively easily in some cases. So there is a review of that and other nonlinear problems that are connected to this. And I gave you a few results from these two papers here. And there are three recent papers with Keaton Ham and Longsho Huang, who is one of my former students and very talented. And I hope she's at UCLA for postdoc, and next year I think she'll be looking for some place. And I hope you just remember her name. She's will be available. And that's all I want to say. And I'll take your point. I don't know if there were a couple of questions, and I kept saying, well, wait till the end. I don't know if I answered those or not, but please feel free to ask them again if you have anything. Thank you.
Thank you. First of all, thank you, Akram, on behalf of everybody. And we have time for questions.
Can I ask a question?
Sure, of course.
I don't know if there is like a line or queue anywhere. I cannot find.
No, please do so.
Okay, so thank you very much for the talk. I just had a few questions. So this subspace problem, could you do it? Can anybody? Well, has anybody looked at it for affine spaces?
Right, so affine spaces are not too, you can use affine spaces. All you have to really add an extra dimension. So if you have subspaces and you want, you have affine spaces and that are, so what you can do is just add a new dimension and take a point, and you can actually transform the affine problem into a subspace problem just by adding one dimension. So do that. Yeah, that's a really good question, right? Because in fact, this is what's done in the motion segmentation.
Okay, so it's
yeah,
not a huge.
yeah.
And for the similarity matrix, so this may be a naive question, but so the entry that's 0 is 0, but non-zeroness doesn't matter how large the value is, like
right. It doesn't matter what these. Let me repeat maybe the question to see if I understand. So if I draw some vectors, of course, hopefully non-zero vectors from the union. And does it matter if some of these vectors are small and some of these vectors are large? This, well, in principle it doesn't matter, but if so.
I meant, I'm sorry, I meant the similarity matrix, not the. I meant for SW.
Oh, if the similarity matrix have large values and small values.
Like, so if you, can you just ignore small values, make them 0? Would you get the same kind of?
That is really a very good question, because that is part of the problem that you need to solve. So if you take a singular similarity matrix, such that the one the shape interaction matrix of Costera. So you have small values and you have large values. Usually, I think in that case you have, I'm going to say, between 0 and 1. But of course, if you have noise, then the question is, well, even if you have no noise, some of these values are small, so are comparable to the noise value. And if they are large, it's okay, but you don't have control over the value of the similarity matrix. So from that point of view, if you take a single similarity matrix when you have noise, it's a little problematic, because you don't have really, exactly like you pointed out, some of these values could be small and they're not noise, they are really similarity. So you want to be able to take many similarity matrices in the case of noise, and somehow from that decide which value you want to put to 0, because in fact it is noise, and which value you don't want to put to 0. And this is basically what we did for these things. So you're right. So it does matter, and this is why it matters when there are noise. And this is why if you have application, you need to take many of them and somehow average in some ways. Yeah.
So sorry, just one last question. So this is this does this have anything to do with when you raise Q to the D max? Like, is this D max a magic number, or would Q squared work better than Q, for example?
Say again. So
you had this.
Yeah, and I square it.
You have in your algorithm, you had at some point you would say, okay, I needed to raise to the power of D max.
Right. The reason why, actually, this is an interesting. Why do we say that? The way we define similarity matrices, it's either they belong to the same subspace. Let's say, then they should be similar, and they don't belong to the same subspace. They should not be similar. Sorry, the similarity is 1. Let's say 1 if they belong to the same subspace, or 0 if they don't belong to the same subspace. Sometimes you can connect this similarity matrix to a graph, actually, and in some sense you want to be able to go from one point of the graph to any other point of the. So you have connected component. Each connected component corresponds to subspace, but sometimes the graph is such that even though you have a connected component, there is no edge or no path. But if you iterate enough, you will eventually go from any point A to any point B in that graph. So that's roughly how, in fact, I'm not sure if I'm being clear. So So the pre similarity matrix is not exactly ones when they are in the same space and 0, simply because not all the paths that we could do from one vector to the next are there. So by iterating this matrix by 10 to the power, we have actually found all the paths possible, and we know that so we won't get this peculiarity where you have two in the same space. It's technical what I'm saying now, but roughly there is a connection between path and some graphs and these similarity matrices, and that's, yeah. I'm sorry, I'm not able to explain it much
I think I can imagine, because when you raise to power, you're counting all the, for example, the entry,
Yeah.
You're counting all the paths of length 2, for example.
Yeah, exactly.
So does that mean that you could raise it to any power more than D max?
You
or
can.
D max was just
You're absolutely right. You can, but there is no reason, I think, because you want to kind of raise it to the least power possible.
Okay, thank you.
Yeah,
Thanks.
Akram, this is Doug Cochran. Can I ask you a couple of short questions here?
Yes, please go ahead.
So the development that you showed today is for mostly real vector spaces, right? Are you aware? It looks to me like it could probably go through almost directly for complex cases. Are you aware of that?
Yes, I think it goes the same way. But the reason, yeah, you're right. I think you're absolutely right. It does not matter whether it's real or but I think we did it just for the real because everything we had was real. You're right.
I'm interested in the complex case because of my, in radar and communications and the carrier, right? The data vectors will be complex. So
I do believe that everything we've done go through for the complex case as well.
You mentioned noise in 3 or 4 times, and in particular in response to the last question that came up. Have you? Is this worked out? Is there one of the papers that you mentioned is a good place to look for any of the tricks that have been done? And are you aware of whether there's been more complete statistical treatment of this kind of problem?
So when we finished that paper, we did not have, we have only tackled so we didn't do the quantitative noise study. However, I believe that at least one of these 2 papers looked at these specific problems when you have noise. Am I right? Is Longshaw or Keaton here?
Hey Akram, it's Keaton. Yeah, so the perturbations paper, which is going to appear in SciMax shortly, it looks at the error incurred of doing a CUR decomposition for a low rank plus noise matrix. So from Doug's question, we didn't apply it to subspace clustering, but you could potentially.
Great. Thanks, Keaton, and thank you, Akram.
Thank you.
Nice talk, by the way.
Thank you.
Hi, Akram. I have a question.
Yeah.
Well, first, thank you for this nice talk.
Thank you, Carlos. That's coming from a friend.
Okay. So you have a bunch of data that you assume that came from some specific union of subspaces.
Mm-hmm.
Okay.
Yes.
So have you considered the case that the same data, you have another union of subspaces that this data belong to? I mean, there is different configuration for the same data. So there are different union of subspaces that contain the same data. So this is a kind of non-unicity of the problem. Have you considered this?
I am not sure I quite understand your.
Well, assume, for example, just
let me try to rephrase your problem. Maybe what you're saying is, suppose I have one plane and one line in R3. And you can say, well, and I pick data from the union of this plane and this line, and you can say, well, the plane and the line are in fact also a subspace of dimension 3. So I can say the whole data come from a subspace of dimension 3, and in that sense, there is a certain non-uniqueness. Would that describe your question more or less what the problem?
Yes, but one comes in. Although you can always get the subspace generated by all the data, but this is an extreme case. But assume you have, for example, 3 independent vectors in R3. So one possibility is that you take 2 in one plane and the next one in one line, or you can take other 2 in one plane and the other one in another line. So this is just 2 configurations for the same data.
I really am not sure. Maybe you can draw that if you can, and that I'm not sure I understand.
Okay, doesn't matter.
The non-uniqueness. I understand about what the non-uniqueness. There is, one can say, well, it's non-unique in the sense that I said, and I think you're basically saying the same thing, but in a slightly different situation. Nevertheless, when you say the independence, at least the independence that I talked about, allow you to. There is really only one possible way of things when you try to. So there is some configuration which is unique, which gives you because of these independence. So somehow you. So for example, I could have 2 lines in a plane, and they can say, well, and a third line perpendicular to these 2 lines, and the first 2 lines form a plane, and you can say, well, we can say either we have a plane or we have 2 lines of dimension 1. So which one it is? And I claim that at least there is a way of saying, well, in that case, it's really 2 lines, even though these 2 lines are so their union is part of a bigger plane, but the data still come from only these 2 lines, and you can actually determine these 2 lines. It's not like you determine just the plane. So from that sense, those are really 2 specifically different problems, and there is a uniqueness.
Okay.
Right. So the points are coming from the line. They're not. But we can talk more about that if.
Okay. Thank you.
Any more questions for the speaker? Well, if not, let's send the speaker again. Thank you, Akram, for very nice talk. And just as an announcement, previously we had Pete Casaza scheduled for next week. Unfortunately, he will not be able to deliver the talk. So we're going to meet in 2 weeks from now with Marcin Baunik's talk. You know, that would be, I believe, March 1st, 2 weeks from today. Thank you.
But Radu, why don't you talk next week?
Well, we'll keep the schedule the way it is. Thank you, Doug.
Thank you, Akram. Excellent talk.
George Washington's birthday.
All right, Victor. Good seeing you.
It's Washington's birthday.
Washington's birthday.
See you all.
Right.
Bye-bye.
Thank you. Thank you all.
Thank you, Akram.
Thank you,
Thank
Akram.
Okay, bye.